Hello all of you. Welcome to the 45th lecture on the course on analysis and modeling in chemical engineering. In the last 2 weeks, we have been discussing about the application of graph theory in chemical engineering. We first discussed how we can use graph theory to represent a flow sheet to figure out the recycle and bypass streams and things like that on a graph, mostly recycle streams, because they make the equations complicated to solve. Using the idea of cyclical nets, we represented the complicated part or the recycle streams, which has to be solved simultaneously. Then we discussed how we can decompose the graph and figure out the order of solving the different equations that we have. And we then applied it to a system of nonlinear equations. And finally, we looked at in the previous lecture how we can apply graph theory in a very different context in analyzing the reaction mechanisms. So in today's lecture, I will extend the idea I started in the previous lecture and talk about something known as bipartite graphs, which can be used for analyzing complex reaction mechanisms. And I will conclude with some other applications of the graph theory in chemical engineering. So what exactly is a bipartite graph? So in bipartite graph, we have two types of nodes. In the previous lecture, we have discussed that the nodes were like intermediates and the edges represented the basically chemical reactions going from one intermediate to the other. But in this case, the chemical reaction is also represented as a node, and that therefore becomes like two kinds of node. One is for the intermediate, the other is for the reaction, right? And the edges now doesn't have the meaning of a chemical reaction. The edges now connect the nodes, as we will see. But the number of edges that we have basically represents the stoichiometric coefficient for the chemical reaction, right? So let's take an example. So we have, let us say, some irreversible reactions in here, and I begin with a acyclic reaction where there are no cycles. So I'm going from, let's say, x1 to x2 to x3 in a series manner to some xn. So what I'm doing, let's say x1 is my first intermediate, then from x1 I undergo the first reaction. So reaction is now a node represented by a square, right? And from that reaction R1, then I go to the second intermediate x2, which is also a node but represented as circle. Then x2 undergoes a reaction R2 and forms x3, and then it continues to x4, x5 to xn, right? You can also have some cycles in the graph. For example, I can go from x1, x2, x3 and xn, and finally from xn I can come back to 1. Therefore, we are forming a cycle, a complete cycle or an oriented cycle going from x1 back to itself, right? So basically, we have formed some kind of a cyclical net where now I can go from any intermediate to any other intermediate. In other words, we have, in our earlier language, a cyclical net of something like nth order. But keep in mind that it is a bipartite graph. So therefore, we have two kinds of node as opposed to what we had earlier. We can also have a non-oriented cycle where we are not forming a loop. It looks like a loop, but it is not. Like the example shown here. So from x1, we have the first reaction R1 giving rise to x2. But then x1 and x2 together takes part in a second reaction R2 to form x3, right? But then this loop is not complete. So I can go from here to here, or I can go from here to here, but I cannot complete the loop, right? So I cannot go back from x2 to x1. That is called a non-oriented cycle or absence of a loop in here. So this graph is representing essentially two different chemical reactions, x1 to x2 with reaction R1 and x1 plus x2 together giving rise to x3, and that is with the reaction R2. We can also do it for reversible reactions. Let us say x1 to x2. Let's say if it is reversible reaction, then I can represent the forward reaction as R1 plus minus plus and backward reaction as R1 minus. So from X1, now I can go to X2 in two ways. One, I can go from X1 to X2 in the forward reaction R1 plus, and then I can come back, from X2 to X1 with the backward reaction R1 minus. And essentially it is forming some kind of a loop or a oriented cycle. I can also have something more complicated like X1 plus X2 giving rise to X3. And again, I can write the forward reaction as R1 plus and backward reaction as R1 minus. Now the forward reaction is X1 plus X2 giving rise to X3, and that is right here. So X1 comes from here, X2 comes from here, participate in the first reaction in the forward direction and forms the product X3. This is this part of the graph, and the reverse is X3 breaking into X1 plus X2. So you see X3 comes to the reaction node R1 minus and now breaks apart into two products X2 and X1, right? And the advantage you see here is now basically after the reaction I can branch out to multiple products, and the reaction basically can happen on the merger of two different reactants, right? That's the advantage the bipartite graph is giving me, that we have two different vertices X1 and X2, and both are basically directed towards or have an edge going towards a reaction node. And similarly for R1 minus, it forms two product. So we have two edges coming out of R1 minus into the two products X1 and X2, and that really makes the complex reactions easier to represent, so as to speak, right? So we have kind of a way in which we can now represent more complicated reversible reactions, and I can apply this idea to, you can imagine, more than two reactants as well. The graph will be naturally more complicated, but the scheme still holds true. Now you can see an example where the stoichiometric coefficient is important. So let us say we have 2x1 giving rise to x2. So from x1, it has to participate in the first reaction R1 plus. So 2x1, 2x2, R1 plus is the first reaction, but two molecules of x1 is participating here. So therefore I have added two edges to indicate that the stoichiometric coefficient is 2, and both edges are pointing in the same direction. I can also put a number on the edge. I can put a single edge, but put a number 2 to indicate that there are basically a molecularity or a stoichiometric coefficient of 2 in this particular reaction, right? Now for the backward reaction, we have x2 participating in the backward reaction and forming 2 moles of x1. So I start from x2, go to the reaction node R1 minus, and R1 minus gives me 2 molecules of x1. So I put a 2 here, or I put 2 arrows here to indicate that 2 molecules of x1 are formed in the reaction. Okay. We can go ahead and have more complicated reaction, something like this: x1 to x2 to x3 to x1, which is all of the steps are reversible. Let us go step by step. So the first step is x1 to x2. The forward reaction is x1 to x2, R1 plus, that is x1 is here, R1 plus is here, and we form x2 here. That is my first reaction. The reverse of the first reaction is x2, R1 minus x1, that is this part in the graph. The second reaction is x2 to x3. The forward reaction for second reaction is x2 to x3, R2 plus, and that is represented here. And the reverse is x3 to x2 with R2 minus, that is right here. And finally, the third reaction is x3 to x1. The forward reaction is x3 to x1 R3 plus, that is shown above in the graph. This goes here like this, and the reverse is x1 R3 minus x3, that is right here. You see, quite complicated reaction mechanisms can be represented by this bipartite graph quite easily. And now you can imagine that once I have this kind of a graph, I can probably do a matrix or some kind of analysis using weights for this graph and basically compute properties as we have discussed for the simpler graphs in the previous lecture. Okay, so let's take an example of this well-known chemical reaction of the oxidation of CO to CO2. This is the overall reaction that takes place, but there are two different mechanisms that is proposed for the reaction happening over the platinum catalyst surface, right? So platinum becomes my active catalyst, whatever I referred as Z in the earlier class, right? So PT is active site, or PT I can refer as an intermediate. Now there are two mechanisms. One is the Eley-Rideal mechanism, in which we say that the oxygen from the bulk reacts with the active sites, in fact two active sites, and it forms two PTO. So basically this is my PT surface. So oxygen basically breaks apart and absorbs on the two nearby active sites, and they are forming therefore two PTO. Now this PTO, each of them, can react with the carbon dioxide, and once that happens they can give rise to CO2, and then PT, it basically goes out of the catalyst and the PT remains bare, right? So we have something like CO2 coming out, and the PT, whatever active site that previously had oxygen, is now bare. So basically we have PT coming back from the reaction, right? So I can write it in two steps. One is oxygen reacting with two PT sites to give rise to two PTO. So 2 PT is giving rise to two intermediates PTO, and then the PTO reacts with CO and forms CO2 and PT. Of course, the reactants and products we don't represent on the graph. We only represent the intermediates on the graph, that is PT and PTO. And in this case, I can represent using the graph. So the first reaction, the forward part is that is 2 molecules of O2, PT is involved. So we put a 2 here, R1 plus, giving rise to 2 molecules of PTO. Then the reverse reaction is, again we don't worry about CO2, we only represent the intermediates. So we start from PTO, 2 molecules of PTO, that's why we have a 2 here, participate in the reverse reaction R1 minus and give rise to 2 molecules of PT. That's my first one. Now the second one is basically something like CO plus PTO. So basically PTO is going back to PT. So we have PTO participating in the reaction, second reaction R2, and going back to PT. And for this particular graph that I am showing, this is considered some kind of an irreversible reaction. In general, it can have both positive and negative, but we are representing as a irreversible reaction. There is another way of doing it, or another possible mechanism where it happens in 3 steps. The first step, oxygen, just like earlier, oxygen interacts with PT and forms 2 PTO. But now this oxygen basically combines with the the CO that is also absorbed on a nearby site. So we have a nearby site absorbed by CO, which is called PTCO. So we have a PTO now and we have a PTCO now, and now they together react, leaving aside bare PT, and CO2 goes in the bulk. So the fundamental difference is that in the first mechanism, Eley-Rideal, we assume that only the oxygen gets absorbed on the platinum surface. CO does not get absorbed. In the Langmuir-Hinshelwood, both oxygen and CO get absorbed, and then once they are absorbed, then they react to form CO2. But once CO2 forms, it goes out, right? So 2PT plus CO2, right? And that is shown somewhere here. So the first reaction, the forward reaction, I start from PT, 2 PT sites participating in the first forward reaction to give rise to 2 PTO sites. Then the reverse of that, 2 PTO sites going back to 2 PT, and the second reaction, CO plus PT to CO, that is somewhere here. So this PT basically reacts with CO, but CO is not on the graph. So the forward reaction gives me PT going to PTCO. The reverse reaction, the PTCO going to PT, and only one molecule is involved. And finally, PTO and PTCO combine in the third reaction. Again, we can assume it to be irreversible, and then they form basically 2 PT, and of course CO2 that is going out, right? So now we can compare these kind of mechanisms by representing them in as a bipartite graph, and we can also analyze things like cycles present in different mechanism, right? For example, I start for this Eley-Rideal case. We can do the subgraphs of this bipartite graph that represents the cycles present in the graph, and in this case we form basically 3 cycles as shown here, which are all subgraphs of this particular graph. And I can also do it for Langmuir-Hinshelwood, and you see that there are many cycles present there. What do the cycles represent? Cycles basically represents a loop, that in what ways we can start from something and come back to the same thing, right? Some sort of an analogy of the recycle in the chemical process we are having for chemical reactions. So we can identify all these cycles present, and if you think about in terms of numerical complication, these cycles are going to make the calculations numerically intensive. So therefore, to identify cycles will help me figure out what is numerically complicated part in my reaction mechanisms. Okay, so this was all about the application of graph theory in the analysis of reaction mechanisms. There are other applications of graph theory in completely different contexts, but still in chemical engineering. For example, graph theory can be used to analyze piping networks, right? So I am showing you here some kind of a piping network of a process plant. And as you may expect that ultimately when you are doing this piping network, the first purpose and the primary purpose is to make sure that you have the connectivity that you desire. But wherever possible, you want to also reduce the cost of the network. And what does the cost depend on? The cost depends on the total weight of the catalyst, right? So now we can basically, starting from this kind of a network, which we can represent as some kind of a graph, we can basically construct some kind of an objective function that represents the total weight of the pipe, which of course depends on the length and diameter of the individual pipe segments, which again, as you can imagine, we can basically assign weights. We can assign weights to the different segments apart from the labels that I want to represent. and we can basically formulate some kind of an optimization problem where we can figure out the net cost of the piping. Also, what we can use it for, and I will take an example, is we can figure out whether two units of the process are connected together or not. We can do some kind of a reachability matrix, and from there we can compute that what kind of connectivity we desire between two units, and then we can look at the piping network, and from there we can figure out how that connection is established, right? Or conversely, if we have a piping connection, we can go back and see that how exactly it is put to use in the chemical process that I am using, right? So those kind of applications can be coming in the piping analysis, but I will not take many examples of that, but at least one example I will take. Okay, so just to take a simple case, we have 6 tank of equal volume, and I'm numbering them, let's say 1 to 6, and they are connected to each other by some kind of a Boolean matrix, right? In the chemical plant, you can imagine these tanks corresponds to different units of chemical process, but this is a much simplified picture. And at time t equal to 0, all the tanks are assumed to be empty. And now water is started being released into one of the tank from an external water tap at time t equal to 0, which is continued at the same flow rate until a water volume equal to total volume of all the tanks is released from the tap. Water can move between the tanks using the connections represented in the above Boolean matrix, just like the piping network I was telling you, and all flows from the tank are from a small orifice at the bottom, and all flows into the tank are from the open top, just to make sure that it can overflow, and the overflow basically goes out. That's why we are keeping the top open, and by doing the orifice only at the bottom, we are ensuring that everything that is inside the tank can essentially go out of the tank, right? If, for example, the hole was somewhere here above the height, then only the part which is above can go out. In order to remove those complications, we assume that the hole is at the bottom and the top is open, so the overflow is very much possible. So now, and the flow out of any tank is equally distributed to all the output streams from the tank, as long as the output streams are going to a tank that is not completely full. And in case any one or more of output stream goes to a completely full tank, flows out of the tank is equally distributed between remaining streams going to the tanks that are not completely full. And in case all the output streams go to completely full tanks, nothing flows out of the tank, right? Essentially, let us say you have 6 tanks like this, and let us say you start filling this tank. What I am saying essentially is whatever this tank is connected to, let us say this one and this one, then the flow can go from here to there and here to there. So let us say some flow V comes here, so V by 2 goes here, V by 2 goes here in a typical setting, right? But as soon as this tank gets full, as soon as the destination tank gets full, then basically the flow stops here and all the flow goes to the first tank, right? So basically flow coming out of the tank gets split into all the destinations equally until the destination tank is full, in which case whatever is remaining, only those tanks gets equal distribution of water. So we have to compute R square, R cube, R4, and then the final question is, will all tanks be completely full after a reasonably long time, independent of the choice of feed tank? If yes, explain your answer. If not, determine using graph theory the possible choices of feed tank and other conditions to ensure all tanks are completely full after a reasonably long time. Right? The question asks you like, I mean, do we have to choose which one should be feed tank, or it can be any feed tank, right? The more will get clear once we look at the graph, right? So let us first do the graph for this case. So I have the Boolean matrix. Let me label it for simplicity. 1, 2, 3, 4, 5, 6. That means from 1 I can go to 2, and from 1 I can also go to 5. From 2 I can go to only 1, and from 3 I can go to 2, and from 4 I can go to 5, and from 5 I can go to 1, and 6 I can go to 3 and 4. So now let us take examples of different feed tanks and see, is there at all any connection from there to the other tanks or not? Because the first requirement is that if I start from any tank, then the whatever is coming out of this should be able to fill the remaining tanks. For this to happen, there should be some connection from this vertex to the other vertex. If not in one steps, then in multiple steps, right? So let us say, for example, I start from 1, I can definitely go to 2, but can I go to 3, right? So from 1 I can go to 5, I cannot even go to 4, right? So there is no way I can go to 3, right? From 2 similarly I can go to 1 and 5, but I cannot go to 6. From 3 I can go to 1, 2 and 5, but cannot go to 6 and also 4. From 4 I can go to 5 and then come back to 1, and from there I can go to 2, but I cannot go to 6. But from 6 I can go to 4, I can go to 3. Via 4 I can go to 5. So I can go from 6 to 4 and 6 to 3 in one steps. I can go from 6 to 1 in 3 steps, 6 to 4, 4 to 5, and then 5 to 1 in 3 steps. And then I can, once I get to 1, then I can go to 2, right? So I can go to 1, I can go to 2, I can go to 4, I can go to 5, and I can go to 3. So starting from 6, I can basically go to every other tank in the problem, right? So I can formally I can compute the reachability matrix for this, and what we should see is 6 is therefore the tank where I should give my input. I can go ahead and try for the other vertices to see if that is true, but I think it should not be true. From 6 only I can go to everywhere else. The reason being that if you look at the matrix here, the column corresponding to 6 contains all zeros. So 6 does not have any ancestors, right? So in order to go for water to go to 6, the only possibility is that 6 gets water itself as the first inlet point. Otherwise, there is no way I can get to 6. The same is not true for any other vertex. They all have ancestors, but only for 6 there is no ancestor. So the feed tank must be 6, right? Now how do I go further? Now I have to see like whether the tank will get full or not. Ideally, we can imagine that if I wait long enough, then all the tanks should get full sooner or later. But if I really want to write formal equations, then we basically have to do material balance on each of the tanks which I am having, right? So let's begin with the sixth tank. So I can write let's say dv6 by dt is the flow that is coming in, which is my input, minus the flow that is going out, that is my output. And let me call this input as something like qf, which is the basically the feed that is coming in, and let me represent that q out as q6 out, just to represent that it is coming out of 6. Now this is going into 3 and 4. So for 3, again I can write the equations. For 3, the flow coming in is whatever comes from there by 2. That is the net input, because this stream that is coming out is 6 out, but it gets divided into 2, minus whatever goes out from 3, that is going into 2. So what is the input, or q3? Whatever is coming out of 3 is q3 out, right? And similarly, I can go ahead and write the equation for all the volumes. Keep in mind that once this V3 gets full, once the third tank gets full, then in that case, my input term here will basically go to 0, because now there is no fresh input coming in there, and that also has to be accounted for. So in general, I am going to have a volume vector, and I am going to have equations for the volume vector in the form dv by dt is some function of their volumes, which is again a vector, and the feed flow rate qf, and we have to solve that equations simultaneously in order to do that. Again, the graph theory can help us figure out the precedence order for solving those equations, right? And what I have not done for this problem is computed r square, r cube, and so on. In fact, I can do that. In any case, I should do it to figure out the r star, the reachability matrix, more formally. But you can do it yourself and convince yourself that 6 is definitely the good choice for the feed tank. So with that, I conclude the week on graph theory, and in the next week we will talk about the separation processes. So with that, I stop here. Thank you so much.